In software engineering, an integer-euro relationship model is a data model for describing the data or information aspects of a business domain or its process requirements, in an abstract way that lends itself to ultimately being implemented in a database such as a relational database. The main components of ER models are entities and the relationships that can exist among them, and databases. Integer-euro relationship modeling was developed by Peter Chen and published in a 1976 paper. However, variants of the idea existed previously, and have been devised subsequently, such as supertype and subtype data entities and commonality relationships. Overview: an entity relationship model is a systematic way of describing and defining a business process. The process is modeled as components that are linked with each other by relationships that express the dependencies and requirements between them, such as, one building may be divided into 0 or more apartments, but one apartment can only be located in one building. Entities may have various properties that characterize them. Diagrams created to represent these entities, attributes, and relationships graphically are called integer-euro relationship diagrams. An ER model is typically implemented as a database. In the case of a relational database, which stores data in tables, which represent the entities. Some data fields in these tables point to indexes in other tables. Such pointers represent the relationships. The three-schema approach to software engineering uses 3 levels of ER models that may be developed. Conceptual data model: this is the highest level ER model in that it contains the least granular detail but establishes the overall scope of what is to be included within the model set. The conceptual ER model normally defines master reference data entities that are commonly used by the organization. Developing an enterprise-wide conceptual ER model is useful to support documenting the data architecture for an organization. A conceptual ER model may be used as the foundation for one or more logical data models. The purpose of the conceptual ER model is then to establish structural metadata commonality for the master data entities between the set of logical ER models. The conceptual data model may be used to form commonality relationships between ER models as a basis for data model integration. Logical data model: a logical ER model does not require a conceptual ER model, especially if the scope of the logical ER model includes only the development of a distinct information system. The logical ER model contains more detail than the conceptual ER model. In addition to master data entities, operational and transactional data entities are now defined. The details of each data entity are developed and the entity relationships between these data entities are established. The logical ER model is however developed independent of technology into which it is implemented. Physical data model: one or more physical ER models may be developed from each logical ER model. The physical ER model is normally developed to be instantiated as a database. Therefore, each physical ER model must contain enough detail to produce a database, and each physical ER model is technology dependent since each database management system is somewhat different. A physical model is normally instantiated in the structural metadata of a database management system as relational database objects such as database tables, database indexes such as unique key indexes, and database constraints such as a foreign key constraint or a commonality constraint. The ER model is also normally used to design modifications to the relational database objects and to maintain the structural metadata of the database. The first stage of information system design uses these models during the requirements analysis to describe information needs or the type of information that is to be stored in a database. The data modeling technique can be used to describe any ontology for a certain area of interest. In the case of the design of an information system that is based on a database, the conceptual data model is, at a later stage, mapped to a logical data model, such as the relational model. This in turn is mapped to a physical model during physical design. Note that sometimes, both of these phases are referred to as physical design. It is also used in database management system. Integer-euro relationship modeling. An entity may be defined as a thing capable of an independent existence that can be uniquely identified. An entity is an abstraction from the complexities of a domain. When we speak of an entity, we normally speak of some aspect of the real world that can be distinguished from other aspects of the real world. An entity may be a physical object such as a house or a car, an event such as a house sale or a car service, or a concept such as a customer transaction or order. Although the term entity is the one most commonly used, following Chen we should really distinguish between an entity and an entity type. An entity type is a category. An entity, strictly speaking, is an instance of a given entity type. There are usually many instances of an entity type. Because the term entity type is somewhat cumbersome, most people tend to use the term entity as a synonym for this term. Entities can be thought of as nouns. Examples: a computer, an employee, a song, a mathematical theorem. A relationship captures how entities are related to one another. Relationships can be thought of as verbs, linking two or more nouns. Examples: an owns relationship between a company and a computer, a supervisor's relationship between an employee and a department, a performs relationship between an artist and a song, a proved relationship between a mathematician and a theorem. The model's linguistic aspect described above is utilized in the declarative database query language ERL, which mimics natural language constructs. ERL semantics and implementation are based on reshaped relational algebra, a relational algebra that is adapted to the integer-euro relationship model and captures its linguistic aspect. Entities and relationships can both have attributes. Examples: an employee entity might have a social security number attribute. The proved relationship may have a date attribute. Every entity must have a minimal set of uniquely identifying attributes, which is called the entity's primary key. Integer-euro relationship diagrams don't show single entities or single instances of relations. Rather, they show entity sets and relationship sets. Example: a particular song is an entity. The collection of all songs in a database is an entity set. The eaten relationship between a child and her lunch is a single relationship. The set of all such child-lunch relationships in a database is a relationship set. In other words, a relationship set corresponds to a relation in mathematics, while a relationship corresponds to a member of the relation. Certain cardinality constraints on relationship sets may be indicated as well. Mapping natural language. Chen proposed the following rules of thumb for mapping natural language descriptions into ER diagrams. Physical views show how data is actually stored. Relationships, roles and cardinalities. In Chen's original paper he gives an example of a relationship and its roles. He describes a relationship marriage, and its two roles husband and wife. A person plays the role of husband in a marriage and another person plays the role of wife in the marriage. These words are nouns. That is no surprise. Naming things requires a noun. However, as is quite usual with new ideas, many eagerly appropriated the new terminology but then applied it to their own old ideas. Thus the lines, arrows and crow's feet of their diagrams owed more to the earlier Bachmann diagrams than to Chen's relationship diamonds. And they similarly misunderstood other important concepts. In particular, it became fashionable to name relationships and roles as verbs or phrases. Role naming. It has also become prevalent to name roles with phrases such as is the owner of and is owned by. Correct nouns in this case are owner and possession. Thus person plays the role of owner and car plays the role of possession rather than person plays the role of, is the owner of, etc. The use of nouns has direct benefit when generating physical implementations from semantic models. When a person has two relationships with car, then it is possible to generate names such as owner person and driver person, which are immediately meaningful. Cardinalities, modifications to the original specification can be beneficial. Chen described look across cardinalities. As an aside, the Barker-Ellis notation, used in Oracle Designer, uses same side for minimum cardinality and role, but look across for maximum cardinality. In Mirais, El-Misri and Navov and others there is a preference for same side for roles and both minimum and maximum cardinalities. Recent researchers have shown that this is more coherent when applied to NR relationships of order greater than 2. In Dallaire al. one reads a look-across notation such as used in the UML does not effectively represent the semantics of participation constraints imposed on relationships where the degree is higher than binary. In Funer it says problems arise if we operate under the look-across semantics as used for UML associations. Hartman investigates this situation and shows how and why different transformations fail. And also, as we will see on the next few pages, the look-across interpretation introduces several difficulties that prevent the extension of simple mechanisms from binary to NR associations. Chen's notation for integer-Euro relationship modeling uses rectangles to represent entity sets, and diamonds to represent relationships appropriate for first-class objects. They can have attributes and relationships of their own. If an entity set participates in a relationship set, they are connected with a line. Attributes are drawn as ovals and are connected with a line to exactly one entity or relationship set. Cardinality constraints are expressed as follows: a double line indicates a participation constraint, totality or subjectivity. All entities in the entity set must participate in at least one relationship in the relationship set. An arrow from entity set to relationship set indicates a key constraint, that is injectivity. Each entity of the entity set can participate in at most one relationship in the relationship set. A thick line indicates both, that is bijectivity. Each entity in the entity set is involved in exactly one relationship. An underlined name of an attribute indicates that it is a key. Two different entities or relationships with this attribute always have different values for this attribute. Attributes are often omitted as they can clutter up a diagram. Other diagram techniques often list entity attributes within the rectangles drawn for entity sets. Related diagramming convention techniques: Bachmann notation, Barker's notation, Express, IDEF1X, Martin notation, Min, Max, notation of Jean Raymond Abriol in 1974, UML class diagrams, Mirais, object role modeling, Crow's foot notation. Crow's foot notation is used in Barker's notation, structured systems analysis and design method and information engineering. Crow's foot diagrams represent entities as boxes, and relationships as lines between the boxes. Different shapes at the ends of these lines represent the cardinality of the relationship. Crow's foot notation was used in the consultancy practice CACI. Many of the consultants at CACI subsequently moved to Oracle UK, where they developed the early versions of Oracle's case tools, introducing the notation to a wider audience. The following tools use Crow's foot notation: ARIS, System Architect, Visio, Power Designer, TOE Data Modeler, DZIGN for databases, DevGems Data Modeler, OmniGraffle, MySQL Workbench and SQL Developer Data Modeler. CA's ICASE tool, CAGen, also known as Information Engineering Facility, also uses this notation. Historically, XA Systems Silverrun LDM also supported this notation. ER diagramming tools: there are many ER diagramming tools. Free software ER diagramming tools that can interpret and generate ER models and SQL and do database analysis on MySQL Workbench, and Open Model Sphere. A freeware ER tool that can generate database and application layer code is the RISE editor. SQL Power Architect, while proprietary, also has a free community edition. Proprietary ER diagramming tools are Evolution, ER Studio, Owen, DZIGN for databases, Magic Draw, Mega International, ModelWrite, Navicat Data Modeler, OmniGraffle, Oracle Designer, Power Designer, Prosa Structured Analysis Tool, Rational Rows, Software Ideas Modeler, Sparks Enterprise Architect, SQL-YOG, System Architect, TOE Data Modeler, and Visual Paradigm. Free software diagram tools just draw the shapes without having any knowledge of what they mean, nor do they generate SQL. These include Creately, YEd, Lucidchart, CalligraFlow, and ER and Semantic Modeling. Peter Chen, the father of ER modeling, said in his seminal paper, "The entity relationship model adopts the more natural view that the real world consists of entities and relationships. It incorporates some of the important semantic information about the real world. He is here in accord with philosophic and theoretical traditions from the time of the ancient Greek philosophers, Socrates, Plato and Aristotle through to modern epistemology, semiotics and logic of Park, Frege and Russell. Plato himself associates knowledge with the apprehension of unchanging forms and their relationships to one another. In his original 1976 article, Chen explicitly contrasts integer-euro relationship diagrams with record modeling techniques. The data structure diagram is a representation of the organization of records and is not an exact representation of entities and relationships. Several other authors also support his program. A semantic model is a model of concepts. It is sometimes called a platform-independent model. It is an intentional model. At the latest since Carnap, it is well known that the full meaning of a concept is constituted by two aspects, its intension and its extension. The first part comprises the embedding of a concept in the world of concepts as a whole, that is the totality of all relations to other concepts. The second part establishes the referential meaning of the concept, that is its counterpart in the real or in a possible world. An extensional model is one that maps to the elements of a particular methodology or technology, and is thus a platform-specific model. The UML specification explicitly states that associations in class models are extensional, and this is in fact self-evident by considering the extensive array of additional adornments provided by the specification over and above those provided by any of the prior candidate semantic modeling languages. UML is a data modeling notation. Part 2 inches, limitations. EA models assume information content that can readily be represented in a relational database. They describe only a relational structure for this information. They are inadequate for systems in which the information cannot readily be represented in relational form, such as with semi-structured data. For many systems, possible changes to information contained are non-trivial and important enough to warrant explicit specification. Some authors have extended EA modeling with constructs to represent change, an approach supported by the original author. An example is anchor modeling. An alternative is to model change separately, using a process modeling technique. Additional techniques can be used for other aspects of systems. For instance, EA models roughly correspond to just one of the 14 different modeling techniques offered by UML. EA modeling is aimed at specifying information from scratch. This suits the design of new, standalone information systems, but is of less help in integrating pre-existing information sources that already define their own data representations in detail. Even where it is suitable in principle, EA modeling is rarely used as a separate activity. One reason for this is today's abundance of tools to support diagramming and other design support directly on relational database management systems. These tools can readily extract database diagrams that are very close to EA diagrams from existing databases, and they provide alternative views on the information contained in such diagrams. In a survey, Brody and Liu could not find a single instance of integer-euro relationship modeling inside a sample of 10 Fortune 100 companies. Badia and Lemire blame this lack of use on the lack of guidance but also on the lack of benefits, such as lack of support for data integration. The enhanced integer-euro relationship model introduces several concepts not in EA modeling, but are closely related to object-oriented design, like ISA relationships. For modeling temporal databases, numerous EA extensions have been considered. Similarly, the ER model was found unsuitable for multidimensional databases. No dominant conceptual model has emerged in this field yet, although they generally revolve around the concept of OLAP-cube. See also, associative entity, concept map, database design, data structure diagram, enhanced integer-euro relationship model, enterprise architecture framework, value range structure diagrams, comparison of data modeling tools, ontology, object role modeling, 3-schema approach, references. Further reading, Chen, Peter. Entity Relationship Modeling, Historical Events, Future Trends, and Lessons Learned. Software Pioneers. Springer Verlag PPA 296 Euro 310. ISBN A3-540-43081-4 Barker, Richard. Case Method, Entity Relationship Modeling. Addison Wesley. ISBN A0201416964. Barker, Richard. Case Method, Tasks and Deliverables. Addison Wesley. ISBN A0201416972. Manila, Hieki. Ra Currency Ea Currency, Kare Jauko. The Design of Relational Databases. Addison Wesley. ISBN A0201565234. Thlum, Bernhard. Entity Relationship Modeling, Foundations of Database Technology. Springer. ISBN A978-3-540-65470-4. Baggy, Sigga. Earp, Richard. Database Design Using Entity Relationship Diagrams. CRC Press. ISBN A978-1-4398-6176-9. External links, The Entity Relationship Model, Toward a Unified View of Data, Entity Relationship Modeling, Logical Data Structures, Getting Started by Tony Drury. Crow's Foot Notation.